Welcome to Organic Chemistry lectures delivered by Sheetal Bhatkurki. In today's lecture, let us look at organometallic compounds. Over a period of time, synthetic organic chemistry has definitely evolved. The boundaries of organic chemistry are constantly evolving. The non-stop emergencies, discovery of new reactions, methods of existing reactions, techniques that enable chemists to prepare increasingly complex structures in ever short time frames with high purity, with high yield has constantly been exploring. Use of catalyst in order to reduce the thermodynamics of the reaction, to increase the product yield and purity and reduce the number of steps in the multi-step synthesis process is constantly evolving. Many of the reactions employ special catalysts that belong to a class of compounds called organometallic compounds. Now let us briefly have a survey of organometallic compounds that are unique, that have unique chemistry and is wide applications in the synthetic organic chemistry. And many of these organometallic catalysts are widely used in pharma industry today for their high percentage of enantioselective compounds. So let us look into few of them. Before we start, let us brush up some organometallic compounds and their chemistry. Organometallic compounds are those compounds containing a bond between a carbon and a metal atom, and that is CM. For example, organolithium compound, that is alkyl lithiums, organomagnesium compounds, organocopper compounds are few examples here, and the highlighted carbon atom is more electronegative than the metal to which it is attached. As a result, each of the highlighted carbon atom is electron rich there. So even the electrostatic potential map of methyl chloride and methyl magnesium is indicated there. The carbon atom is electron deficient here in methyl chloride, and methyl lithium the carbon atom is electron rich there. So that is clearly seen there, right? In methyl chloride, chlorine atom withdraws the electron density away from the carbon, whereas in lithium, methyl lithium, lithium is giving the electron towards the carbon, thereby increasing the electron density at the carbon rather than at the lithium, therefore making carbon more nucleophilic in nature. Indeed, lithium is also both very strong base and a strong nucleophile. Right? This property makes organometallic reagents particularly useful in the synthesis of a source of nucleophilic carbons. And for any carbon metal bond, the magnitude of the partial negative charge on the carbon atom is dependent on the metal that we are preferring there. So considering the electronegativity value of element that withdraws each of the whether it is giving electron towards the carbon, that is what is very much essential for us. So the difference in electronegativity between carbon and the metal, say for example magnesium, if I take, electronegativity of carbon is 2.5, whereas magnesium is 1.2, is much greater. Carbon has much greater electronegativity, almost 2 times than the magnesium. Similarly, between copper and carbon has 2.5 and copper has around 1.9. Again, the copper has more electronegativity. As such, organometallic compounds, say RMgX, which we write it as a Grignard's reagent, are much more stronger nucleophile and stronger base than a organocopper reagent. Right? So that's why we see that acid halides react with 2 equivalents of organomagnesium, that is Grignard's reagent. But acid halide will react with only 1 equivalent of organocopper reagent. right? Fine. Also we have seen that reactivity between the reagents is very much essential for us, and organocopper reagents are effective Michael donors rather than acceptors, while organomagnesium reagents are not. They are not Michael donors, right? So for example, in the following alpha beta unsaturated transformation, what we are seeing, that is Michael reaction, cannot be efficiently achieved with a organomagnesium reagent. It cannot be achieved with the organomagnesium reagent more effectively when compared to the what we see in other Michael reactions, right? Yes. Use of transition metal has evolved and is been evolving. Even still today, people are trying to make a better form of the transition metals, right? Modify the transition metals. So there is advancement happening even. The use of transition metal has revolutionized in the field of synthetic organic chemistry, and is been by modifying the transition metals much more being much more reactive, much more favoring the reactions, increasing the purity and percentage of the products, etc. In that case, the ionic nature is very much important. Of the ionic nature of organometallic is very much important. So let us see first organolithium and organomagnesium compounds. Organolithium and organomagnesium compound both exhibit a carbon metal bond with a high degree of ionic character. Organolithium and organomagnesium compounds behave very much like a carbon anions, and we know that carbon anions are strong base as well as strong nucleophiles. In fact, alkyl lithium and alkyl magnesium are among the strongest base and the strongest nucleophiles, right? For which Grignard's reagent, right? Grignard's, who awarded a Nobel Prize in the year 1912 for this purpose of piece of work, right? This work, which is widely used even up to till today also. But today there are much more sophisticated organometallic metallic catalysts like palladium and all, which has come up and which has conquered a greater position in the industry, right? But before that, it was the Grignard's reagent which was much preferred actually, right? All the reactivity of Grignard's reagent is similar to the reactivity of organolithium reagent also. That is one point. So both of them are on the same line, right? Magnesium as well as lithium, which we will be seeing little later. Organolithium reagents can be prepared by treating with the organohalides with two equivalents of lithium. The R group of the organohalide can be alkyl, aryl, vinyl, anything as shown here. So we have alkyl, aryl, bromobenzene and vinyl chloride we have here, right? The transformation is believed to occur via radical intermediate and generally non-polar solvents such as hexane or diethyl ether is typically used there, right? If we look into the Grignard's reagent, right, Grignard's reagents can be prepared by treating with the organohalide with the magnesium in an ether as a solvent. It can be diethyl ether, which result in insertion of magnesium ion into CX bond. So it becomes RMgX bond from RX. Formation of organolithium compounds and formation of organomagnesium compound is believed to occur through the radical reaction, radical intermediate only. The R group can be, again I am saying, is alkyl, aryl and vinyl. In both the cases it can be. Generally what we see is iodides are more reactive over bromine and bromine over chlorine. Although bromides are used more commonly because bromides are less expensive and less toxic than the iodides, and so bromides can do their role actually, what is required there, right? So they are much preferred. That's why we have boronic acid and all of bromide, bromide only, right? Bromide boronic acids, etc., which we will be covering later. The preparation of Grignard's reagents require the use of solvents such as diethyl ether that can function as a Lewis base and stabilize the Grignard's reagent as it is being formed. Grignard's reagent and organolithium reagent both are very strong base, and each of them react rapidly with the water to give a hydrocarbon. As indicated here, the carbon anion can easily drag the proton from the water molecule and form a new bond there. The enormous difference in the pK value between water and the hydrocarbon, that is, the water is around 15.7, whereas the hydrocarbon will result up to 50, right? Will renders the process irreversible, and a similar irreversible reaction can occur even with the magnesium halide or with the lithium halide when treated with the deuterated water also. So this reaction is also called as deuteration, right? So Grignard's reagent or organolithium reagents will not only react with water or deuterated water, but they will also react with any functional group that exhibits weakly acidic protons such as OH, NH, SH, C double bond CH or carboxylic acid. Therefore, none of this functional group can be present in the starting halide, alkyl halide, right? So a Grignard's reagent cannot be prepared if an OH group is present in the compound. Please note that. And one more point is that the solvent can be either diethyl ether or THF. Generally, we should ensure that to remove the water traces, amount of water traces, if they are there, we have to remove that, right? Because the presence of even trace amount of water will consume the Grignard's reagent upon its forming. So the preparation of organolithium or the Grignard's reagent must be performed in anhydrous condition, anhydrous solvent, right? That care should be taken. Preparation of Gilman's reagent. Lithium dialkyl cuprates are also called as Gilman reagent. These are nucleophilic in nature, so nucleophile will react with the carbon electrophile in the selective manner, right? They will react in very selective manner. So lithium dialkyl cuprates are often used, and in situ they are used and prepared by treating with organohalide with the lithium to give organolithium, followed by treatment with the treatment of organolithium with the cuprous halide. We get Gilman's reagent, that is lithium dialkyl cuprate. And secondly, what we see is an halide is converted to a ketone upon treatment with the dialkyl cuprate. In contrast, treating an acid halide with a Grignard's reagent initially gives a ketone that cannot survive under the condition or its formation. Therefore, the ketone is further attacked by a Grignard's reagent giving alcohol. The R group can be alkyl, aryl or vinyl, even in case of lithium dialkyl cuprate. It can be anything there. So remember that the Gilman reagents are nucleophiles, and as such they will attack a variety of electrophiles. That's why Gilman's reagents are widely used in many reactions. Gilman's reagent is lithium dialkyl cuprate. This Gilman reagent will react with organohalide to give a product in which the R and R dash groups are to be coupled together. So R and R dash can be coupled together. This coupling reaction is also called Corey-Posner or Whiteside's-House reaction, and can be performed in diethyl ether or THF as the solvent at a low temperature. because of the thermal instability of the Gilman reagent, so temperature has to be low. And the halogen can be bromine, iodine, chlorine. They are reactive, they are more reactive, therefore can be used. The R and R dash group can be any organohalide, which can be methyl or primary or vinyl or aryl. And R dash cannot, one thing is R dash cannot be a tertiary alkyl halide, as elimination product predominates there. So even secondary alkyl halide can be generally ineffective, but okay to certain extent when compared to tertiary alkyl halide. So more preferred would be primary. Nevertheless, even cyclic halides are also used. The coupling process is very stereospecific because it is observed that it is observed to proceed with the retention of configuration at each of the carbon double bond carbon units. So in the Gilman reagent and in the organohalide both, right? So we expect it to be very stereo specific. However, the mechanism is not well understood and are likely to depend on identity of the R dash as the reaction condition. And a coupling process can occur in presence of variety of functional groups including ketone, esters, amides. That's why it is preferred also, more preferred also. Let's see Simon-Smith reaction and carbenoids. Compounds with copper and zinc bond are called organo-zinc compounds, and they can be prepared in a much same way as that of the Grignard's reagent are preferred. Especially an alkyl halide is treated with an metal zinc which insert itself into CX bond and forms CZNX bond. Ether or diethyl ether is used to stabilize the resulting organo zinc compound. Carbon is more electronegative than the zinc, so induction gives the carbon atom a partial negative charge. This was the same case in Grignard's reagent also, right? Although Grignard's reagent have much greater ionic character than the organozinc reagents, even organozinc reagents are widely preferred. They are also polar covalent rather than ionic when compared to other organometallic. Copper zinc is more polar. Polar covalent. One very useful organozinc reagent is with iodomethyl zinc iodide. I repeat, iodomethyl zinc iodide, which is ICH2ZnI, developed by Howard Simmons and Ronald Smith. That's why we call it as Simmons-Smith reagent also. When together they were working for DuPont, so they developed this organometallic reagent. So this reagent can be prepared by treating with iodomethane with a zinc copper couple, which was formed by treating with the zinc dust with copper chloride as well as copper sulfate. The structure of this iodomethyl zinc iodide is actually more complex than the scope of our understanding, and therefore Smith and Simmons demonstrated that alkene can react with this metallic reagent, that is iodomethyl zinc iodide, to form three-membered ring. That is cyclopropanation will happen. So cyclopropanation will happen whenever we are treating here. So we can see that couple of examples indicating here where the formation of cyclopropane is indicated. So cyclopropane derivative is formed, and we know that the cyclopropanation process is observed to be very stereospecific with the configuration of the alkene being preserved in the cyclopropane product as well. So if I start with a trans alkene, then I am ending into a trans cyclopropane. Cis will give me a cis cyclopropane. So it is very stereospecific. Transition metal elements can react with molecules or ions, give rise to a complex that exhibit useful properties and behavior. A large number of transition metal complexes have been developed for the use as catalyst over past several decades. The evidence of the incredibly use of catalyst has transformed the field of synthetic chemistry to a greater height. Indeed, palladium catalyst has been among the most common catalysts that available to practice synthetic organic chemist, and much more molecules have been synthesized using palladium catalyst. Palladium reacts with a variety of molecules or ions called ligands to give transition metal complexes. For example, in the reaction here, we have two ligands, that is chlorides, reacting with the palladium, forming CPDC, react with two equivalents of triphenyl phosphane, giving 4 ligands in the end product. So the end product, we can see that there are 4 ligands. Ligands donate electron density to vacant p orbital, giving rise to bond PDL that are generally polar covalent. These ligands are weakly associated with the palladium center, and as a result, the number of ligands that are bonded to palladium can change depending on the conditions. Although the transition metals are more stable when they achieve the electronic configuration of a noble gas. We have also seen the behavior with the second row elements. Although second row elements can only accommodate 8 valency electrons, the valence shells has only s orbital and 3 p orbitals, each of which can accommodate 2 electrons. In contrast, the valence shell of transition metal elements can accommodate 18 electrons. The valence shell has 1 s orbital, 3 p orbitals and 5 d orbitals, and thus can accommodate 18 electrons and will follow 18 electron rule for transition metals. A transition metal is said to be coordinately saturated if it has all 18 electrons. For example, in PDPH3 4 times, that is triphenyl phosphate tetra triphenyl phosphate palladium features a palladium atom that is coordinately saturated, because palladium has 10 valence electrons when the oxidation state is 0, as it is in the case, and each of the ligand provides 2 electrons for a total of 18 electrons. Complexes with the palladium atom have fewer than 18 electrons are said to be coordinatively unsaturated, and such complexes will often function as reactive intermediate in the reaction. Therefore, synthetic transformation that utilizes palladium complexes as catalysts are much preferred. The first reaction with the palladium catalyst is Stille coupling. John Stille developed a powerful and a versatile transformation using palladium catalyst, which is today called as Stille coupling, which occurs in presence of suitable palladium catalyst in the reaction between a organostenone, that is organotin CSN, and an organic electrophile to form a new carbon-carbon sigma bond. This coupling reaction between R and R dash can be achieved by using a different kind of palladium catalyst, such as tetra triphenyl phosphine palladium, in which palladium atom has an oxidation state 0. Alternatively, palladium with 2 complex can be used where the oxidation state of palladium is +2, such as palladium diacetate as well as palladium chloride. Stille coupling. Stille coupling occurs when there is presence of suitable palladium catalyst, which will react with organotin and organo electrophile to form a new carbon-carbon bond. This coupling reaction between R and R dash can be achieved by a variety of palladium catalysts such as PDPH thrice 4, in which palladium atom has oxidation state 0, and alternatively we have palladium 2 complexes such as PDOAC2 as well as PDCl2 PPH3 twice, which are nothing but palladium diacetate or palladium dichloride triphenyl phosphate. When a palladium 2 complex is used, it is converted into palladium 0 complex, which is believed to function as an active catalyst. In Stille coupling process, each of the coupling partner, that is R and R dash, can be aryl or vinyl groups, and X can be any halogen, say chlorine, bromine and iodine. Or it can be a triphthalate, that is OTF. When both the partners are aryl groups, the product obtained is a biaryl system, and so on. Stille coupling provides a convenient method for joining two aromatic systems into biaryl system. When one coupling partner is aryl and the other coupling partner is a vinyl, the product obtained would be a styrene kind of compound, and so on. Preparation of organo stability and stability of organo tin compound. Many organo stannins are commercially available and they can be stored for a period of time, as they are not sensitive to oxygen or moisture, so they can be preserved. They can also be readily prepared from Grignard's reagent upon treating with tributyl tin chloride. Organo tins are useful because they are extremely selective in their reactivity. In presence of palladium catalyst, they can react with the aryl and vinyl halide even when other functional groups are also present, including that of carboxylic acid, amides, esters, nitro compounds, ethers, hydroxy compounds, ketones, aldehydes, etc. Therefore, the process can be performed even when a coupling partner bears the functional groups. Let's look at the mechanism of Stille coupling. First step is the oxidative addition. The electrophile, that is Rx, after the X has been leaving group, which is ready to leave away and go, so R becomes electrophilic in nature, will react with the active palladium complex, giving a new complex in which both R and X are each bonded to directly to palladium, are directly bonded to the palladium. So we can see here, instead of R, it is R dash indicated here. During this addition process, the oxidation state of palladium increases and the process is therefore called as oxidative addition. The ligand L, as indicated, are not identified because their identity can change during the process. So convention is to show only the crucial reacting groups, that is R and the halide and the palladium. Next step is the transmetallation. In transmetallation, the R group of the organostylane or organotin is transferred to palladium complex and takes place the halide group. The term transmethylation indicates that the R group was transferred from one metal, that is tin, to another, and that is palladium. So from tin it is been transferred to palladium, the R group. This step is generally the rate determining step of the overall coupling process. So the rate determining rate of the transmetallation is directly dependent on the identity of the R group. That is what R group I am going to prefer. Therefore, vinyl, aryl, alkyl, benzyl and alkyl. So is the rate. That means vinyl group migrates most rapidly when compared to an alkyl group. So if you have an alkyl, then please convert it into vinyl and then make it to undergo Stille coupling. Or you convert it into aryl and then convert it into let it go to for Stille coupling. That's what it exactly means, right? Because vinyl is greater, have more rate of reaction compared to aryl, aryl over allyl over benzyl much higher than the alkyl. The least is the alkyl. So the low rate of migration of alkyl group is exploited during the Stille coupling, which typically employs organotin with the three alkyl groups. Either all the three are bulkier groups or so on. So we just play on with the R group, or convert them into aryl vinyl and then make the reaction to happen. Let's go for the third step now. Reductive elimination. Reductive elimination. The R and R group are released from the palladium complex with the formation of a new sigma bond between the R and R dash. That is, they are coupling partners now. During this process, the oxidation state of palladium is reduced, thereby generating the active palladium catalyst PDO, that is PDL2. So that's why it is reductive, right? Elimination, because both R and R dash are eliminated from the catalyst, from the transmethylation state. Therefore, it is elimination. So there are three stages. First step is oxidative addition. The second step is transmetallation, and the third step is reductive elimination. Comprises a catalytic cycle that consumes the starting material, that is organotin and a organoelectrophile, produces the coupling product, that is R and R dash or new CC bond, and generates the catalyst back. Therefore, we represent this in a cyclic form. So we can see that it is represented in a cyclic form. Curved arrows do not appear there, right? Instead, we show a complete arrow moving there, because mechanism of each step of catalytic cycle is likely dependent on the condition. Throughout this rest of all the reactions that we are going to encounter now in this session, we will not be using the movement of arrow, but we will be indicating the complete arrow there, because we are going to deal with the catalytic cycle. Catalytic cycle will be shown without curved arrows. Please note, catalytic cycles are not shown without curved arrows. One more important palladium catalyst using reaction is Suzuki coupling, named after Professor Akira Suzuki, which is very much similar to the stellite coupling, but organoboron compound is used instead of organotin compound. It's very much like a stellate coupling. A palladium catalyst such as PDPH3 4 times is employed, right? That is tetraphenyl triphenyl palladium catalyst is employed. But Suzuki coupling also requires basic condition. For Suzuki coupling, the coupling partners are organoboron compound and an organic electrophile, giving rise to a new RR, that is CC bond, as the coupling product. In the organoboron compound, the Y group can be alkyl group, alkoxy group, or a hydroxy group. Depending on the method of preparation, these compounds are called organoboranes, boronic ester, or boronic acid, respectively. Just as the stellate coupling, the R group of the organoboron compound can be vinyl, aryl, or allyl. Now let us see the structure of organic electrophile in Suzuki coupling. Again, just as in the stellate coupling, R dash can be anything, as I said. It can be aryl, vinyl, or alkyl. Generally, aryl and vinyl is the more preferred. Even allyl is fine, right? And can be a halide or a triphthalate, that is OTF. Although chlorides are generally much less reactive or preferred. The following are all suitable organic electrophiles for Suzuki coupling, that is aryl iodide, vinyl bromide, and a vinyl triphthalate. Here are the two examples of Suzuki coupling, wherein we can see that a aryl group and a alkene group is been coupled there. Similarly, we have here again alkene coupled to an alkene group, right? Now, Suzuki coupling offers several advantages compared to Stille coupling. One significant advantage is that the ability to use an alkyl borane in the coupling process. So, alkyl boranes can be more preferredly used. So, this provides a general method of making a bond between sp3 and sp2 hybridized center. So, Suzuki coupling therefore provides greater versatility than the Still coupling in the type of bonds that can be used. To sum up, if I say that CC, that is between two diphenyls, if I take, then it is sp2 and if I take between a phenyl and a alkene, it is sp2 and sp2, right? It is again between, if I take between a alkene with a alkene connected by a single bond there, then it will be sp2, right? So on, right? Whereas in Suzuki I can take between an sp2 and sp3, like a phenyl group connected to an alkyl group. Similarly, an alkene connected to an alkyl group, which can again be sp2 sp3, right? With this, there are other advantages of Suzuki coupling. For example, the ease with which inorganic byproducts are removed, as well as lower cost and lower toxicity of organoboron compounds relative to the organotin compounds, and purity of tin also has to be checked there. So, however, there is one disadvantage with Suzuki coupling relative to the Stille coupling, that is, it requires of the basic condition. Under this condition, if either coupling partner has to be a keto or a aldehyde group that pairs a alpha proton, like aldol type of reaction if you recall, and can occur to give undesirable products. So both Stille coupling and Suzuki coupling are frequently applied by practicing the synthetic synthetic organic chemists, and the choice can be determined, will generally be determined by the details of the particular transformation that is to be that is desired there, right? So for Suzuki coupling, particularly useful of making conjugated dienes, and the process is observed is to be stereospecific there. That is, the process generally proceeds with a retention of configuration of each carbon C double bond C unit, right? Preparation of organoboron compounds for using Suzuki coupling. Organoboron compounds can be readily prepared from a variety of starting materials. For example, vinyl boronic acid esters and vinyl borane can be prepared via hydroboration of alkyne using catechol borane or 9-BBN respectively. Similarly, we can prepare alkyl boronic esters and alkyl boranes can be prepared via hydroboration of alkene using the same catechol and 9-BBN respectively. We can do it, right? And also aryl boronic esters can be made by treating with the corresponding aryl lithium compound with the trimethyl borate, BOMe3, trimethyl borate. Now let us look into the mechanism. Please note that I have indicated the cyclic structure here. The way in which we used to write the mechanism is different because there we used to show, in regular case we used to show the movement of arrow or electron moving, but here we are showing you the complete arrow momentum, and it is in the cyclic form. Therefore, in cyclic mechanism we do not show with the movement of arrow, right? Whereas we indicate complete reaction there. Suzuki coupling is believed to occur via a mechanism that is very much similar to the Stille coupling, three steps. The catalyst cycle begins with the oxidative addition and ends with the transmetallation and reductive elimination in Stille. Whereas in Suzuki coupling, which occurs in basic condition, there is an additional step that occurs as a part of catalytic cycle. And in this additional step, we will call it as displacement, right? So the X group, that is halide group or a triphthalate, what is being used is displaced by an alkoxide ion, thereby rendering the palladium complex more reactive towards transmetallation. So the first step is indicated here as oxidative addition. So we can see that the oxidative addition is happening, displacement is happening, transmetallation is happening, reductive elimination is happening. So if you look at it, the first step, it is indicated there that the palladium catalyst is undergoing oxidation and it is going to react with the electrophile, and therefore electrophile R dash and X are binding to the palladium. In the next step, in presence of the base, displacement will happen and the X is displaced by the OET there, right, the base there, and in the next transmetallation should happen. Therefore the organoboron compound will react with the intermediate there and will form a RPDR bond, right. So in the next step, elimination of both the groups such that both the groups will couple with one another and form a new bond, which is RR dash. So elimination will happen. At the same time, the palladium is getting reduced. Therefore, reductive elimination. During Suzuki coupling, the base plays a very crucial role. Please note, it activates the catalyst for the transmethylation step. But just not that, but also activates the organoboron compound by converting into organoborate anion, which undergo transmethylation more rapidly. The common use bases are sodium hydroxide, sodium ethoxide, etc. Suzuki coupling has a wide application in synthetic organic chemistry because it can be used in presence of wide range of functional groups. Aldehydes and ketones can give aldol type of reaction in basic conditions. This issue can be mitigated by using milder conditions. A variety of modified reagents and conditions have been developed further to enhance the versatility of Suzuki coupling in synthetic organic chemistry. Suzuki coupling in general is inefficient when the organic electrophile is an alkyl halide, and under the basic condition required for Suzuki coupling, an alkyl halide can undergo undesirable elimination via E2. Nevertheless, recent advancements has begun to see that this problem has been solved. Especially special conditions and reagents have been developed that could allow for the coupling between the two sp3 hybridized centers under certain circumstances. These developments and many other continue to improve the significant versatility of the Suzuki coupling. Suzuki coupling, please note, in 2010 has been received Nobel Prize. Let's look into another reaction, that is Negishi coupling. The Negishi coupling is another versatile reaction that utilizes an organometallic species containing zinc, aluminium or zirconium. The organometallic reagent is coupled to an organic electrophile in presence of transition metal catalyst, say zinc or palladium or nickel. Palladium or nickel, right? So primarily on the major subset is the palladium catalyst. Coupling of organo-zinc reagent. So we can see here RZnX will react with R-X in presence of palladium catalyst, resulting in formation of a new RR- bond, that is CC bond, and zinc halide is eliminated out. So this reaction is named after Professor Negishi, who also got Nobel Prize in 2010, along with the Suzuki coupling and Heck coupling, because all working on the same catalyst, that is palladium catalyst, different sort of palladium catalyst. Organo-zinc compounds are generally more reactive than the corresponding organostannine and organoborane. in part due to the low electronegativity of the zinc, which has around 1.6 relative to tin, which has around 1.8, and boron has 2. The greater difference in electronegativity between the metal and the carbon will give rise to more polar carbon metal bond, and thus is the more reactive species. This increase in reactivity can lead to an efficient Nagashi coupling reaction where the analogues, that is Still and Suzuki reaction, fail to undergo. Right? So a disadvantage of the increased reactivity is that many organozinc reagents are sensitive and especially water sensitive. So necessity the use of equipment to ensure that the reaction runs in a very inert atmosphere has to be taken care. However, recent advancement have come up. They have prepared salt stabilized organozinc reagents which can be used, and even then inert atmosphere is preferred, but however we can manage off, right? Not very much stringent to have a inert atmosphere. So again here electrophile can be electrophilic halide can be any R group can be anything like vinyl, aryl, alkyl, anyl, or benzyl or allyl. This is also very highly stereoselective process reaction where the configuration of C double bond C unit is retained. Up to around 99% we get the retention of the configuration. Only when a nickel transition metal catalyst is used, the stereospecificity is slightly diminished, that is from 99% we can expect it to be around 90%. Organo aluminum, when used, then the aluminum has only one vinyl group and two alkyl groups. As in Still coupling, the vinyl group migrates more rapidly from the aluminum to the palladium in the transformation step. In the transmetallation step, thus resulting in selective coupling of the vinyl group over the allyl group. So general order of carbon electrophile is allyl over benzyl, benzyl over vinyl, vinyl over aryl, aryl over alkyl. In the following Nagashi reaction, the vinyl iodide is reported to be 100 times much more reactive than the primary alkyl iodides. The stereoselectivity of Nagashi coupling is often dependent on the metal catalyst. For example, coupling reaction between a E-vinyl organo aluminum and a Z-vinyl iodide, as indicated here, will result in the formation of E and Z configuration in the end product. So use of palladium catalyst results in high stereo selective process where the configuration of each carbon double bond unit is retained. That's what it should be retained when compared to the Still coupling. The scope of effective Nagashi reaction also depends upon the combination of coupling partners. So it depends on what are the two coupling partners that we are going to use. That is organic electrophile produces the desired cross coupling products in high yield. For example, alkyl and alkynyl zinc are known to successfully couple with a variety of organic electrophile in presence of transition metal catalyst palladium, resulting in the end product R C triple bond R. Nagashi can be used to form a new bond between two sp3 hybridized carbon, which was hindered in Suzuki. Often with the use of unconventional catalyst and or additives it can be attained. Preparation of organozinc reagent. Organozinc reagents are prepared in one of the two ways. One of the most common way is the organolithium compound you take, that is make a carbon anion, or take a Grignard's reagent, make a carbon anion with zinc halide, where halide can be chloride or bromide or iodide. Alternatively, it can also be prepared by addition of zinc metal to the ether solution of aryl or vinyl or alkyl halide. Palladium catalyzed cross-coupling reactions using organometallic reagents containing aluminum, zirconium or copper can oftenly be greatly accelerated by the addition of zinc chloride or zinc bromide. The addition of this zinc chloride or bromide can increase the rate of reaction from several folds and can produce a successful cross coupling that would otherwise fail in presence of the additive. Also, it can undergo in situ reversible transmetallation with zinc halide to produce the more reactive organo zinc reagent. Therefore, these all are the recent modifications or advancement in the Nagaishi coupling. Let us look into the mechanism. The accepted mechanism for Nagaishi coupling is a catalytic cycle analog to that of Stille coupling or Suzuki coupling. Oxidative addition of the organic electrophile to active palladium species results in new oxidized palladium complex. So the first step remains the same, that is oxidative addition. In the transmetallation step, the organic group from the organo-zinc reagent is transferred to palladium complex and ZnX2, that is zinc halide, is expelled out. Finally, in the reductive elimination step, the coupled products are obtained and the active palladium complex is regenerated. So again it is 3 steps: that is oxidation addition, transmetallation and reductive elimination. Nagaishi coupling in synthesis. The carbon-carbon bond formation of using Nagaishi coupling provides access to diversity of molecular structures and widely used in the preparation of many natural products as well as synthetic pharmaceutical drugs. For example, synthesis of carotenoid including vitamin A is been synthesized using Nagaishi coupling. So wide variety of compounds can be synthesized to attain high stereo selective product. Heck reaction. In 1960, Richard Heck discovered and developed the coupling reaction between a aryl vinyl and a benzyl halide and an alkene in presence of an appropriate palladium catalyst in presence of a base. This process replaces a vinyl hydrogen atom of an alkene with a R group. The Heck reaction is particularly useful as there are no other general ways for achieving this type of transformation directly. The reaction is most efficient when organohalide is iodide, even though bromide and triphthalate are also reactive, but iodide is more preferred in the Heck reaction. Please notice that in each case here the newly formed carbon-carbon bond is 2 sp2 hybridized centers, which is a characteristic feature of the Heck reaction. We have seen other reactions that can only create a carbon-carbon bond between 2 sp2 hybridized carbon centers, such as in Stille or Suzuki. But in Heck reaction, this has a greatest advantage that it does not require the preparation of a organotin compound or organoboron compound. Indeed, the Heck reaction is one of the most widely used method for CC bond formation. And for this pioneering work of palladium catalyst coupling, Richard was also given Nobel Prize in 2010 along with the Suzuki and Nagaishi. Like Stille and Suzuki coupling, Heck reaction can be achieved with a catalyst such as palladium, that is PdPH3 4 times, in which palladium atom has a oxidation state 0. Alternatively, PD2, that is palladium diacetate, can also be used, where palladium 2 complex is used and is converted to palladium 0 complex, which is also going to which is believed to function as the active catalyst. Thereby, a commonly used is base triethylamine, although other bases are often used, including sodium acetate or potassium acetate or sodium carbonate, etc. can be used, but widely used is the triethylamine. Alternatively, triethylamine is used. Now, coming to the alkene, if we look it into in Heck reaction, the reactivity of alkene decreases with increasing the substitution, and the highest yields are obtained for ethylene or monosubstituted ethylenes rather than a more substituted ethylene. Particularly, the most reactive monosubstituted ethylene are those in which the substituent is electron withdrawing rather than electron donating. When a monosubstituted alkene is treated with a Heck reaction, the process generally observed is highly regioselectivity. The R group being installed at less substituted vinyl position of alkene. That's why it is regioselective. Let us look into the mechanism. The Heck reaction occurs via a catalytic cycle, and it is believed to be comprised of several stages. For each stage of the catalytic cycle, the mechanism may vary depending upon the conditions. So, curved arrows are not shown here. In the first step, the catalytic cycle, the organohalide Rx will react with the active catalyst via oxidative addition, which is very much similar to your Stelli and Suzuki coupling. The resulting complex will then react with the starting alkene, adding R and PD across the pi bond in a syn addition. The R group being installed at a very less substituted position. Therefore, it is regioselective. Now, the resulting adduct then undergo a conformational change via CC bond rotation, followed by a syn reductive elimination that gives the product. The catalytic cycle is going to be completed when the base removes the hydrogen halide via reductive elimination to generate back the active catalyst. So, here also it is 3 steps only: oxidative addition, the next one transmetallation, which is a syn addition and regioselective, and the third one is even the CC bond rotation will happen and reductive elimination will happen with the generation of the catalyst back. The same has been indicated here in the cyclic structure. So, we can see that the first step, that is oxidation addition, is happening, then syn addition followed by CC bond rotation, then syn elimination, and last reductive elimination. Alkene metathesis, also called olefin metathesis, is one of the most powerful synthetic technique used by organic chemists. The term metathesis is derived from the Greek word meta and thesis, which is change and position respectively. Meta means change, thesis means position. Alkene metathesis is characterized by redistribution of carbon-carbon double bond, that is change in the position of carbon-carbon double bond is what is alkene metathesis, which is given by Robert Grubbs in 2005, and he is awarded Nobel Prize for this alkene metathesis. Here, many catalysts have been developed for achieving the alkene metathesis, and all these catalysts contain a transition metal element with a double bond to a carbon-carbon atom. That is, instead of Cm, it is going to be now C double bond M, and they are often called as metal alkyl dienes. Please note, they are often called as metal alkyl dienes. Schrock catalysts are based on the molybdenum, while Grubbs catalysts are based on the ruthenium. So because Grubbs gave it first, so ruthenium catalyst usages, we can find ample of examples. Even Schrock is been used, molybdenum is also used, right? Newer reactions we can see with the molybdenum also. In each case, variety of ligand can be used, and most utilized catalyst are shown here is Schrock catalyst, Grubbs catalyst. Again, Grubbs has two newer catalyst, which we call it as which is again using rhodium itself and ruthenium itself, sorry. It is a second generation catalyst, but using a cyclohexyl or aryl. So R group now it can be instead of PCY3, he is using now a cyclohexyl or a aryl group there. The carbon C double bond M bond is indicated here in the red color in the all the three, that is in Schrock catalyst and Grubbs first generation and second generation catalyst. When an alkene is treated with a metal alkyl diene catalyst, that is a Grubbs catalyst say, the two vinyl positions of the alkene are separated from each other and the fragment then can be recombined. The process is particularly effective in effective case that involve terminal alkyls like mono-substituted alkene or 2,2-disubstituted alkene. In such cases, one of the product is ethylene gas, which bubbles out of the solution and is effectively removed from the product mixture. The evolution of ethylene gas drives the reaction towards the formation of one alkene with the excellent yield. Let us look into the mechanism of alkene metathesis or olefin metathesis. Alkene metathesis can be divided into two stages. The first stage is when the catalyst react with the starting material to give the two different metal alkyl diene complex. That's an intermediate, which we can label them as intermediate A and B. Each intermediate is formed via 2+2 cycloaddition, which is followed by the fragmentation process. Please notice that the byproduct formed along with A and B also, right? Only small amount of these byproducts are formed because the metal complexes is only present in a catalytic amount. Once A and B are formed, intermediates are formed, they function as the catalyst for the second stage, where starting material is converted into the product. When both A and B can react with the starting material alkene, so let us first explore the reaction between intermediate A and then starting alkene, and later on with the intermediate B. So first with the intermediate A, if we look here, notice that the cycloaddition step has been drawn to show the metal being installed at the less substituted carbon of the starting alkene. If instead the metal has been installed at a more substituted carbon of the starting alkene, the result would be production of the starting alkene and intermediate A. Although this can entirely occur, it does not involve a net change, so it can be ignored. That is starting alkene plus A giving rise to starting alkene plus A itself. Now let's explore the reaction between intermediate B and the starting alkene, which regenerates intermediate A and produces a ethylene gas. Please notice that the cycloaddition step has been drawn to show the metal being installed at the more substituted carbon of the starting alkene. If instead the metal has been installed at less substituted carbon of the starting material, the net result would be the production of the starting alkene and intermediate B. Once again, this can certainly occur, but it does not involve net change. Starting alkene plus intermediate B once again will give me the starting alkene plus B itself, so it can be ignored. Please note, stage 2 of the process can be thus be summarized as A is converted to B or B is converted to A. That is with conversion of starting alkene into the product, or conversion of starting alkene into ethylene in case of B. In this way, the starting alkene is continuously converted into the product and ethylene. So this catalytic cycle is summarized here. The entire mechanism is described in a cyclic form now. Metathesis has been widely used in ring closures and ring openings. When the starting material is a diene and the reaction is conducted in dilute solution which favors the intramolecular process, alkene metathesis is served to form a ring there. So we call it as ring closure metathesis. And a variety of ring size can be attained through this method. Now similarly, ring opening metathesis can also be achieved in presence of ethylene. Under these conditions, a cycloalkene can be opened to give a diene with the introduction of two methylene groups. Now, alkene metathesis can be achieved in presence of wide variety of functional groups that includes aldehydes, ketones, acids, esters, amides, amines, sulfonates, ethers, alcohols, etc. So this features contributes to the enormous application of olefin metathesis in synthetic organic chemistry. Wide variety of products are synthesized using olefin metathesis, having wide applications in industry. With this, I covered the organometallic compounds. Basically, I dealt with the Still coupling, Suzuki coupling, Heck reaction, Negishi reaction, and lastly with the alkene metathesis. Thank you.